All right, a deep cut of going back to handouts 6 through 10. Some of these I will go faster than others, and I don't think I'm going to do 1 through 5. All right, some projectile 2D motion. Consider a 1D problem with the acceleration is 2 meters per second squared. If the velocity starts at -1 meter per second, what is the velocity after 5 seconds? Here, that is using the fact that v as a function of t is v naught plus a t. So you could plug those in, you can get some sort of number. When the acceleration is constant, the kinematic equations apply. It therefore looks something like this. There is some point, in this case it looks like it is a half a second. When it crosses 0, this instance, if I were to describe this, this might be, say, moving to the left, at which point then the velocity changes sign. So this might be when, say, the object starts moving to the right. This would be an example where something stops and turns around. Position as a function of time, it starts here, might look something like this, say. Now suppose the problem is this: the acceleration is given by a vector, the velocity begins at that, find the final velocity for 5 seconds. So in this case, with vector expressions, the kinematic equations still apply, but now the vector, v, is the initial vector plus the acceleration vector times t. So in this case, it is -1, 0 plus 2t and 1t, or the vector -1 plus 2t, 0 plus t. It gives you the vector as a function of time. If you plug in 5 for t, you get both the x and the y components for the velocity. Suppose I go to right, so which is their acceleration, the vertical or horizontal? There's no acceleration in the horizontal because these dots are equally spaced apart from one another. The green dots corresponding to the position in the horizontal direction. This delta x is always the same for the same delta t. The velocity is therefore constant, the acceleration therefore is 0. Well, in this case, delta y is getting bigger as time goes on. Therefore, the velocity is changing, there is an acceleration. The kinematic equations would apply because the accelerations are constant in both directions. In one direction it's g, one direction it's 0. The melon is launched with initial height, h has the initial velocity of blah. What is the position vector as a function of time? So in this case, the kinematic equations might say that the position r is given by the position of x and y as a function of time, which by the kinematic equations might be the initial x plus the initial velocity in the x times t plus 1/2 the acceleration in the x direction t squared. And then similarly for the y component. That is the general answer. In this case, it looks like it starts at initial height of h, has no initial vertical velocity, and then accelerates downward due to g. So the vertical component might look something like this. The horizontal component might look something like that. There's no acceleration in the horizontal direction and starts at 0. Fed up, you throw your textbook towards a tall wall at a speed of 25 meters per second at an angle 40 degrees above the positive axis. The wall is distanced 22 meters away. So it might look something like this. Write down the x and y initial components. So in that case, it is 25 meters per second squared, but then the horizontal direction would be cosine of 40, and the vertical direction it'd be sine of 40. Both of those are positive, so we're taking up and to the right as the positive directions. Write down the velocity, and this would be, I guess, v naught x, v naught y as a vector. Write down the velocity vector as a function of time. So Vx and Vy would be the initial Vx, and there's no acceleration in the x direction, but then the y direction, there is an acceleration, so you have the kinematic equation. Write down the position vector as a function of time, so that's similar to what I did before, so I'm not going to bother. How long does it take for the ball to reach the wall? So in that case, you could ask, since x equals x naught plus v naught xt, or you can think of this as delta x equals v naught x times t. If we set this equal to d, we know this, we can solve for this for the time. That gives us a time. At what height above your initial throw does it hit the wall? In this case, you could say, okay, y equals y naught plus v naught yt minus 1/2 gt squared. And you can plug in the t you got from the previous problem to get your height. Has it passed its point of maximum height? You don't actually have to do an entirely new projectile problem. You could remember that v naught in the, v in the y direction is given by v naught in the y direction minus gt. You could plug in the t you got from 2 problems ago. If this entire thing is positive, that means it's still going up. If this entire thing is negative, that means the ball is going down. And so that's saying whether or not it's on this side where it's still going up, or if it's past its highest point and now it's starting to descend. Knowing that at the highest point, its vertical velocity is 0. Its horizontal velocity, perhaps, is not 0 in the case of projectile motion. We talked through this one to death, and this one is too involved for an exam, so I'm not going to go through it. Couple conceptual questions. Is it possible to be accelerating while traveling at a constant speed? Since it says constant speed, yes, uniform circular motion would be an example of this. You're accelerating because you're constantly changing direction, and acceleration is a vector. So if you change direction or magnitude, that is a change. Is it possible to round a curve with 0 overall acceleration? No, for what I just said. You are constantly changing direction, therefore you are constantly accelerating. Your velocity is constantly changing direction, that is. Is it possible to round a curve with a constant magnitude of acceleration? Yes, if it's uniform circular motion. If you're rounding a curve at a constant speed and the curvature is the same radius, you would have a constant magnitude of acceleration. Magnitude is directionless, so that's perfectly fine. While riding a moving car, you toss an egg directly upwards. Does the egg tend to land back in your hand if the car is moving at a constant velocity? Yes, that was the demo. The car is decelerating, braking. No. The egg keeps flying forward. And then the car is turning a corner. No. Accelerations break, right, the demo in a sense. And that gives the egg. What kind of centripetal accelerations are experienced at the equator of the Earth? So in that case, it's v equals v squared, a equals v squared over r. I give you r. How could you find v in this case? Well, you know that if this was a bird's eye view, so here's maybe the North Pole. If someone on the equator goes around one circle every 24 hours, so you know that the velocity is the full circumference of the Earth divided by 24 hours would give you the velocity. Then you can plug those in. Several train tracks are being considered. Some are semicircles, some are quarters. A train can fall off the tracks if it experiences an acceleration too great. If a train takes each track at the same speed, rank the tracks. So at the same speed implies it's doing something that's like uniform circular motion. The V's are the same for everything. So in this case, it's whichever one has the largest radius is the safest. So in this case, let's see, least risky to riskiest. So in this case, 4 is the least riskiest. 3 has a smaller radius. 2 is an even smaller radius. And 1 has the smallest radius. Even though 1 is just a quarter, this curve right here, you can think of it as a circle. You know, that's kind of like this compared to the other semicircles. Whether it's a semi or a quarter doesn't really matter, besides perhaps how long they're in the turn. But number 1 is the riskiest in terms of accelerations. Person stands at the end of a merry-go-round and is rotating about the merry-go-round center. A person is moving with constant speed and experiences a centrifugal acceleration of blah. Okay, so a top-down view. Standing on the south point of the ride. Here's the person. Draw the position and the acceleration vectors. So I put the origin at the center of the merry-go-round like it says. The position vector points out from the origin to the person. The acceleration vector points towards the center. Repeat the previous problem, I had the person saying somewhere else. The takeaway is that the centripetal acceleration always points towards the center, as must be required for centripetal acceleration. What is the radius of the merry-go-round? That's just identifying that it's v squared over r equals a. You were given 2, you were given v and a, you can solve for r. This sort of stuff we kind of saw again. I guess what we're saying is the frequency is 5,000 rotations per minute. Oh, sorry, per second. So the period is 1 over the frequency, or 1 over 5,000 seconds. We hadn't done this yet, but if I want to talk about the angular frequency or the angular velocity, I could do something like that and calculate the angular frequency. What kind of acceleration, description, and magnitude does a speck of dust experience at the edge of the blue ray? So in this case, it's still undergoing uniform circular motion. So a speck of dust will feel itself pulled in towards the center, even though it itself is moving, say in this direction, as it rotates in a circle, if it's rotating at uniform circular motion. Yes, I suppose one could ask, you know, this is assuming that the dust is lodged and is not moving relative to the disk. If the dust were able to slip on the disk, there might be a tangential component that is not pointing towards the center, but that maybe is pointing towards, essentially is pointing to keep the speck of dust rotating along with it, which might be from friction between the disk and the dust. Is this acceleration greater or less than what is felt at the edge of the center hole of the disk, which has a diameter of blah? So in this case, the acceleration, v squared over r. In this case, we can actually use our stuff we now know, that v can be written as the angular velocity times r. That's squared over r. So this is the same thing as omega squared r. Everything on the disk is rotating with the same angular velocity, but the linear velocities are different. The speck of dust at the outer edge of the disk has to traverse a larger circumference in the same amount of time. It is moving much faster. But in this case, this shows that the acceleration is greater the farther out you are. For the same angular velocity. Here's a demo where I attach the ball to a string placed on a horizontal table. I swing the ball around in a circle on the table. The acceleration of the ball is provided by a string. What concepts of learning that apply here? Is this uniform circular motion, projectile motion, both or neither? So this is uniform circular motion because there is a acceleration. You know, this is a top-down view. There's an acceleration from the string, or I think forces. There's a force from the string that is pulling the ball towards the center. There's an acceleration towards the center, but since it has a velocity that's perpendicular, the velocity vector changes direction, but not in magnitude. And as long as it keeps moving in a circle, this will always be the case. Right, if I do this vertically, it's not uniform circular motion because when the ball's at the top, it feels both the acceleration from the string and the acceleration from gravity pulling down. Yet when the ball is at the bottom of this vertical circle, gravity is still pulling down, but the acceleration is now pointing up. So the magnitude of the acceleration is not the same throughout this vertical circle. So it is not uniform circular motion. If I were to do this and let go of at some point, it would then stop doing uniform circular motion and would immediately go into projectile motion. In that case, the acceleration from the string would vanish, and it would just be negative g always pointing down, which is projectile motion. These are the same sorts of things. All right, forces. Let's see. So we played around with that first one. Right, force. Go back to the definitions of forces. It's not a quantity that can be given to some object, like energy. It only occurs at points of contact and requires contact unless it's a long-range force like gravity. Velocity is experiencing forces. Remember that force is proportional to acceleration. That's F equals ma. So in this case, if I replace all the F's with A's, I can think about whether or not this is speeding up or slowing down. So remember, when things are pointing in the same direction, that is speeding up. So this is purely speeding up. In the second case, the acceleration and the velocity are closer to being parallel than anti-parallel. The angle between them is less than 90 degrees. So this is also speeding up, and also V is changing direction. V will start to veer closer to the direction that A is pointing. Given enough time, V will move to be parallel to A. So in this case, this is only changing direction, not magnitude. And then this is slowing down and changing direction. Given enough time, the velocity vector may eventually start pointing closer to the same direction as A and might eventually become parallel, which at that point, then the velocity vector will start getting bigger and bigger. And then yes, F equals ma is that last part. Force diagrams. Draw a box around the object that is your system and identifying all the things that are touching the object. All right, so for example, if my system is the red ball, and I draw my system, I draw a circle around the red ball and look at what is touching the red ball. In this case, the people are not touching the red ball. The red ball is experiencing a force from Slinky 1 and from Slinky 2. The people do not exert a force on the red ball. And then gravity, of course, is the one long-range force. In the case of D, the lamp has gravity pulling down. Then it's also in contact with the ropes. So there might be some tensions from those ropes. And that's it. That's the only things that are touching the lamp. gravity being the exception. Similarly, this box on the ramp, it is in contact with the ramp itself. So there's a force from the ramp or from the surface of the ramp. It is also touching the string, so there's some tension from that string. And then there is gravity pulling down. Then I think these are all the same, yes. Let's see, I toss a ball into the air. The ball is at the highest point, what forces act on the ball? So again, this is getting to the point that when the ball is at its highest point, it has perhaps momentarily stopped moving up or down. In this case, it's still moving horizontally, but gravity is nonetheless still acting. It's still accelerating, even if I threw the ball vertically upward. Even if I threw the ball vertically upward and it came to rest momentarily at the top, it would still be experiencing an acceleration. V equals 0 does not mean A equals 0. Similarly, right after it leaves my hand is no longer touching the ball. My hand is no longer exerting a force on the ball. This came up in exam 2, I think, when the box was being launched up the ramp from the spring, one of the problems at the end. Once the box stops touching the spring does nothing to the box. People were saying that the spring was doing work on the box while it was moving up the ramp. No. While it's moving up the ramp, it was only touching the ramp. So there was a normal force from the ramp and then gravity. In that case, gravity was the only thing doing work. You don't impart force to an object. You're floating on a pool of water, drifting at a constant horizontal velocity. What forces act on you? So in that case, gravity is pulling down on you, but you're touching the water, so there must be some force pushing up on you, and they better be balanced, else you're going to start accelerating up or down, so you're either going to sink or start flying. So, you know, if no vertical acceleration, which essentially says your vertical velocity is 0 and stays 0, then that means that some of the forces in the vertical direction better add up to 0. You weigh less when you are in water. So we got to be careful. So weight corresponds to what a bathroom scale would read. So if you were, say, standing on a bathroom scale in water, gravity would be pulling, you know, what are you in contact with? Well, gravity's pulling down on you. You're touching the ground, so you're touching the bathroom scale. The normal force is the bathroom scale. But then there's also water, the buoyancy force, that is pushing up on you. So again, buoyancy plus the normal force must be balancing the downward forces, which is just mg. In this case, the normal force is not just your weight, mg, but it's mg minus however much buoyancy force you're experiencing. Imagine a scenario where 2 kids are on a seesaw. They both have the same mass. The seesaw does not move. This implies there's no net acceleration. What are the forces that prevent the seesaw from accelerating? In this case, acceleration equals rotation. You know, we can now think of this in terms of torques. For equilibrium, that means that the torque about the axis of rotation, which is the center, must be in balance with one another. In this case, the fact that there is no rotation, you can also just think of that it's an equilibrium with the forces. So the kid on the left is in contact with the seesaw. So there's some force from kid on the left and there's some force from kid on the right, which is pushing down on the seesaw. And then the ground is pushing up on the seesaw because the seesaw is also in contact with the ground. In the vertical direction, these forces must balance one another. You could also think of this in terms of torques. If you were looking just at the plank that the kids are sitting on, that better also be, the torques about that axis of rotation better also add up to 0. All right, so it says this has a magnitude of 3 newtons. Force 2 is the same magnitude but points down. Some of these vectors to sketch was the components of this net force. So then we're just back to vectors. The force 1 is 3 newtons pointing to the right, 0 in the vertical direction. And it might be 0, -3 for force 2. If down is negative, the sum of the forces then is 3, -3 newtons, are the components of these two vectors. What is the acceleration vector for the rock? So then the acceleration vector is just take this force vector and divide by m. So in this case, it looks like it's 1 -1 meters per second squared if it's 3 kilograms. You could also convince yourself that this does indeed point 45 degrees below the horizontal axis. Now we get into some Newton's law problems. What force is required to accelerate a 500 kilogram rocket sled from rest to some final velocity in 1.8 seconds? First, find the acceleration you need to go from that to that, then use that to determine what force is needed. Draw a free body diagram to help. I think I was since it was a sled, I was intentionally thinking that this was vertical. So there might be some force that is, if there's a rocket here, that is ultimately pushing the box to the right. So a free body diagram, in the horizontal direction might be the rocket. And there might be gravity and a contact force, but they're happening in the vertical direction, so I don't really care that much about those. The acceleration, if it's uniform, we could just do as delta V over delta T. If it's starting from rest, then this is just the final velocity divided by the delta T, since it's -0 technically in the top. Then this force from the rocket then is the mass of the rocket times this acceleration. An elevator car has a mass of blah. It's supported by a single cable. What is the tension in the cable when it's moving downward at 12 meters per second? So again, I draw my system. Identify any contact forces. So it's touching the spring, or the tension, I guess, that's pulling up. Then there's the long range force of gravity. And that's it. So if I define up to be positive, that means that the sum of the forces, which is the tension force plus the gravitational force, a sum here because it's vectors. But then if I throw in the coordinate system, that's T minus mg. The sum of the forces equals the mass times the acceleration. But if it's moving downward at 12 meters per second, that means there's no acceleration. The velocity is not changing. This is it. This is 0. So then T equals mg. What is the tension during the time the elevator is brought to rest with a constant acceleration of 4 meters per second? So in this case, if it's moving downward initially, in order to bring it to rest, we've talked about how that requires an acceleration that is anti-parallel to slow something down. So if my system is the exact same thing, nothing has changed there. My free body diagram is the same, but now there's an overall acceleration upward. So in this case, the sum of the forces equals the mass times the acceleration. If up is positive, this is the tension force plus the gravitational force equals the mass times the acceleration. Bringing in the coordinate system, T is positive upward minus mg because it's downward equals m times the acceleration upward. In this case, the tension must be m, not just mg, but mg plus a. The tension has to do more. It not only has to balance out gravity, but then it also has to accelerate the thing upward. So it also has to be pulling up with an additional force. Consider the setup below is attached to a rope. Calculate the magnitude and direction of all the forces acting on the box. Use a coordinate system that is aligned with the ramp. So again, if my system is the box, I draw my system of, a circle or whatever around, and see that it's in contact with the ramp. It's in contact with the string. And then there's gravity that's pulling down, and that must be it. So in this case, I would say that there is a contact force from the ramp. You can call it N if you so desire. There is a force from the string. We'll say that there's some tension. And then there's gravity, which is pulling down, vertically downward on the object. And then we talked about how if this is theta, then this is theta. And so then you just have to break things. Now my system, my coordinate system, I guess, is kind of x, y, but it's at an angle where x is along the ramp and y is perpendicular to the ramp. Let's have up the ramp and off the ramp be the positive directions. In that case, the tension looks like it's only along the ramp itself pointing upwards, and there's no vertical component. Again, vertical meaning off the ramp. What I drew as y there. Similarly, the normal force does not point along the ramp, but it does point perpendicular to the ramp. Positive off the ramp. The only one that's a little bit different is the force due to gravity, which it looks like there's a component that is parallel to the ramp, and that looks like it's negative mg sine theta. Then there's a component that is parallel or perpendicular to the ramp, but pointing into the ramp, so negative mg cosine theta, based on the triangles that are drawn here. The triangle to acknowledge is this triangle, which allows you to get the vertical component, and then this part right here is the horizontal component. So in that case, the sum of the forces equals the mass times the acceleration, which must be 0 if the box is stationary and remaining stationary. So then that's tension plus gravity plus the normal force equals 0 if I add them all up as vectors. Then if I bring in their vector expressions, that says T0 plus negative mg sine of theta, negative mg cosine of theta, plus 0n must equal 0. Or that if I look just at the top row, t minus mg sine theta equals 0. Then it looks like negative mg cosine theta plus n equals 0. So then this just says that the tension is mg sine theta. It balances out the part of the gravitational vector that points along the ramp, and then the normal force, the surface force, what the bathroom scale would read is mg cosine of theta. If the cord is cut, what is the resulting acceleration the box experiences? It does not accelerate perpendicular to the ramp. It does not sink or fly off the ramp, but it does experience now an acceleration parallel to the ramp, what I'm calling the x direction. So in this case, it's the x component of gravity plus the x component of the normal force equals the mass of the box times the acceleration of the box in the x direction. This is mg sine theta plus 0 equals max, where that ax is negative g sine theta. negative, which implies it's moving in the negative direction of my coordinate system, which if you look is down the ramp. If the rope is instead replaced with a spring constant of yada, how much does the spring extend? In this case, the spring points along the ramp, so there's only an x component, not a y component, and it is equal to minus k, the amount of stretch that occurs. In this case, you have to be careful because it will stretch down the ramp so that delta S is actually also negative, which is, we will see that play out. So essentially this is saying negative k delta S minus mg sine theta equals 0 if everything's in equilibrium. You notice that delta S is mg sine theta, negative mg sine theta divided by k. Negative because the negative direction was defined as down the ramp. So it's saying that stretching down the ramp. We consider this problem, but now with another identical box. What are the tensions in both strings? So that's fun. So free body diagram, I would say for the red box, gravity pulls down, tension pulls up, and then the normal force points away from the ramp. Then for our green box, gravity still pulls it down. There's a tension is touching two strings. So there's a tension pulling up the ramp and a tension pulling down the ramp. And then it also has a normal force. We don't need to know about Newton's third law, but the math will ultimately show that these two tensions are exactly the same, as must be the case. They are a force pair, so they will have equal magnitude, opposite direction. We talked about that when we essentially said that the tension in the string is uniform throughout. That essentially was working in Newton's third law. So I could just call both of them T1, but they're pointing in different directions. So in this case, for the red box, right, again, the vertical component, again, by vertical, I mean away from the ramp, ends up just being the same as it was above. The normal force is mg cosine theta. In the horizontal direction, only the tension pulling upward is balancing the gravitational pull going downward, and that must equal 0. So then you can figure out what the tension in the first string is, or the string that's connecting the two boxes. This will be positive because it's pulling the red box up. For the green box, the normal force is exactly the same. But now there's the tension 2 pulling up, tension 1 pulling down, and then also it has gravity that is also trying to pull it down. So it's something like this. T2 then equals T1 plus mg sine theta, or 2 mg sine theta. That tension has to exert twice as much force because it is, in a sense, holding up both boxes. Suppose you have a box attached to the rope is pulled with a force of 12 newtons. What's the acceleration on the box? Seems a lot easier than the ones we just did. You're pulling with some force. F equals ma. This is just a one-dimensional problem, so you don't have to worry about vectors. Essentially, if that's 12 newtons and that's 4 kilograms times the resulting acceleration, the acceleration is 3 meters per second squared. Oh, now I remember where we're going with this. Forces can be redirected through pulleys. when the pulley is frictionless and massless, you can assume no forces are exerted on the pulley. We now know that when the pulley itself has mass and physical extent, it has rotational inertia, and you have to make some effort to get it to rotate. Do I want to do this? This is essentially the same as the two boxes attached by a string together. So I think I'm not going to do this one. Now forces with friction. In Galileo Hall, a box remains stationary while a force is applied, the angle is given, the surface is rough. Draw a pre-by diagram for the setup, write down the magnitude of each force as well as for the maximum possible static friction force. So again, there's my system. The push is at an angle. Gravity is downward. This push is pointing towards the right as well as downward, but pointing towards the right. So it's going to want to accelerate the box to the right. Friction doesn't like that, so it's going to push to the left to try to keep everything stationary. In this case, it seems like it's remaining stationary. If it's remaining stationary, then this, and then there's a contact force. If it's remaining stationary, then there can't be any net acceleration, or the net force is 0. In the vertical direction, that means the normal force points up, mg points down. Then there's also this push. There's also a vertical component from this push that's also pointing down. If you were to break F sub p into a horizontal and a vertical component, that must equal 0. Essentially, the normal force in this case is mg plus the push sine theta. It again is not just your weight. It is your weight plus this additional little push. Like I'm standing on a bathroom scale, or you're standing on a bathroom scale and I'm pushing down on your shoulders. The scale reads a larger number. In the horizontal direction, you got the horizontal component of the push. Will have to the right be positive. And then there's a resistance from static friction. So then in this case, the static friction, since nothing is moving, is just equal to whatever F push cosine of theta is. That is not necessarily the maximum amount of force that can be exerted. Fs max is the static coefficient times the normal force, or the static coefficient mg plus F push sine theta. Remember, the maximum static friction force is the maximum amount of force that friction can provide to keep the thing stationary. Else, everything starts to slip and things will start to move. Then it becomes kinetic friction instead, which is just a constant. But remember, static friction can be anything up to this maximum value. Suppose the angles increase to a larger value. Determine if the forces increase or decrease. So you're given how everything depends on sine and cosine. You can reason that out. What is the condition for a box to slip and move despite there being friction? We just talked about that. 3 experiments are done in Galileo Hall. 3 different forces are applied. The force magnitudes are yada. In each experiment, the box remains stationary. Rank the forces according to the value of static friction. So again, the more force that is being resisted, the larger the static friction. So since it's remaining stationary, it's static friction every time. This is just getting to the point to really re-emphasize that static friction is a variable. It can be whatever it needs to be to keep everything stationary. A block of mass m is pushed up a rough ramp. The applied force F is directed parallel to the ramp while the box is in motion. Draw a free-body diagram. If the box moves up the ramp at a constant speed, write down an expression for the applied force. So there's my system. Gravity points straight down. I realize my screen just went away. There's a force from the push. And then there's a force from friction that is resisting that motion along the box. I don't know why this requires me to restart it. So a force push up the ramp, and then there's friction. In this case, kinetic friction, because things are moving, parallel to the surface down the ramp. And then there's the surface force, or the normal force, in this case, perpendicular to the ramp. If v is constant, the acceleration is 0. So the sum of the forces acting along the ramp must also be 0. We know the sum of the forces are 0 perpendicular to the ramp, else the box would leave the surface or sink. But even along the ramp, this implies that the sum of the forces better add up to 0. So in this case, I could just, I know that F push has a component along the ramp. I know gravity has a component along the ramp. And then I know friction has a component along the ramp. And those three forces better add up to 0. The horizontal components, rather. So along the ramp, there's F push, which I'm going to call the positive direction to be up the ramp. Gravity is going down the ramp. So that's minus mg sine. And then friction, kinetic friction, is, is also going down the ramp. In the vertical direction, the normal force points off the ramp, but then gravity is pointing into the ramp. And those are the only forces along, perpendicular to the ramp. So then that gives us what the normal force is. It's mg cosine theta. So you can plug this in. So it's Fp mg sine theta minus mu sub k mg cosine theta equals 0. What are we looking for? Write down an expression for the applied force. Okay, so we're done. So then it's mg sine theta plus mu k mg cosine theta. Suppose now the direction of motion and the applied force are reversed and now point down the ramp. How does the free body diagram change? What needs to be true for the box to continue moving down at a constant speed? So now it's moving down this way. So in this case, the free body diagram, there's still gravity. There's still the normal force. It says now the push has been reversed. But now friction is resisting the motion, so now friction is pointing in the opposite direction. In this case, it's slightly different because now friction is before up here, friction and gravity were working together to resist the push. They were both pointing down the ramp while the push points up. In this case, gravity is working with the push to make the box move down the ramp, and so the friction force has to work against both of them in order to create a constant velocity. So in this case, again, if down is negative, it ends up just being negative F push, negative mg sine theta, plus mu sub k mg cosine theta equals 0. So the value of F push changes because some of the signs of the forces have changed. Now the push is pointing down, gravity is pointing down, but now friction is pointing up. Versus here where the push was pointing up, gravity is pointing down, and friction was pointing down. Yes. the problem I alluded might show up again, and then it did on an exam. So you're pushing a box against a wall. The coefficient is yada and the coefficient kinetic is blah. If the box is initially stationary, does the box start to slip or move? So the free body diagram, if I identify my system as the box, the free body diagram is there's a force of the push, there's the force from the wall, there's gravity trying to make the box move down, which friction may resist, and points up. In this case, the surface force, the normal force per se, is the force from the wall. So in this case, what we're calling N is F wall, because the normal force is defined as the surface force. In this case, the surface is a vertical wall. So in the horizontal direction, since nothing is moving, that just means that the normal force is just the force of the push. They must be in balance, or the force of the wall, which is the normal force. Vertically, if things are stationary, then that means that static friction is pushing up while gravity is pulling down, and they better equal 0. So then the static friction that's necessary is equal to mg. And the question is, does it move or not? Is F static equal to mg less than or equal to mu static times the normal force, or mu static times the force of the push? If that's true, the box remains stationary. If that's not true, the box begins to slip, and then you switch over to kinetic friction and then use that to calculate what the vertical acceleration would be. Newton third law problems. Right, the nice thing is that if you define your system smartly, and now that we've done momentum, maybe this is more obvious, you can do things much simpler. So if I define my system as this entire mass of all 3 boxes, tension 2 and tension 3 are forces acting on the boxes, but they are all internal to the system. Thinking about momentum, remember momentum only changes if there is an external force acting on the system. All the internal forces by Newton's third law cancels everything out and doesn't say what's going on for the system as a whole. In this case, if I define my system as the 3 boxes as a whole, with the 2 strings T2 and T3 inside the system, then the only force that matters is T1. The free body diagram in this case is just T1 pulling to the right, and then the sum of the masses, then there's the gravity of everything and the contact force, which is not super meaningful in this case. So in this case, I could say that T1 equals the mass of the system, m1 plus m2 plus m3, times the resulting acceleration of the system, box 1, 2, 3 as a whole. I give you T1, I give you all the masses, you can figure out the acceleration of the entire thing as a whole, if you wanted to. Now the idea is if we look at each box individually, so I guess, do I need this number? So I guess it's 25 divided by 1, 2, 3. So I guess this is divided by 6. I should have made that a nicer number. Well, that's some number for A of the system. Which is helpful because every box itself is individually accelerating at this particular acceleration. If they had different accelerations, then that would mean they would move relative to one another. And the strings might go slack, for example, or the strings might snap if they were not all accelerating together. So for M3, it has gravity, it has a normal force, which the vertical motion is not going to matter in this case. then it has tension 3 pulling it to the right. For M2, there's the vertical things, it has tension 3 pulling it to the left and tension 2 pulling it to the right. Then M1, the verticals, it has tension 2 pulling it to the left, it has T1 pulling it to the right. Again, these are the Newton third law pairs, which we are kind of inherently assuming by saying that the tensions are the same. So in this case, for M1, for the first box, T1 is, if I say to the right is positive. T1 pulls it to the right, T2 pulls it to the left. That must equal the mass of box 1 times the acceleration of the system. In this case, T2 is T1 minus M1A system, it looks like. Or similarly, if I look at mass 3, looks like T3 is pulling to the right. That's the only force acting in the horizontal direction. So then that must be equal M3 times the acceleration of the system. And then if you put those together, you get something that's self-consistent with the second mass, for example. And then, or I guess we were trying to find the tension, so I guess this is a way to find all the tensions. We could have also did this, by the way, if we did not know the acceleration of the system, we could have also written down 3 equations that would have, 3 tensions and 1 acceleration. And since you know the tension in T1, that would give you 3 equations with 3 unknowns. You could find the other 2 tensions and the acceleration all simultaneously. This essentially is the exact same problem, except now it's not a string, but it's just a contact force. If you wanted to do this for M3, again, I'm going to ignore the vertical components. The force pushes M3 to the right, but then the force of box 2 touching box 3 pushes it to the left because box 3 and box 2 are touching. There is a contact force. M2, force of box 3 on box 2 is pushing to the right. It's touching the green box. And then it's also touching the red box. So the force of box 1 on box 2 is pushing it to the left. And then M1, it is only touching one of the boxes. So it's feeling a force from box 2 on box 1. The third law pairs, that's a pair, and that's a pair as a result. You can do the same thing like you did above, and you can get the individual forces for each of them, for each of these internal interactive forces, just by identifying this as Newton's third law. Right, for example, you could say, if the system is the entire thing, then the only external force is a force pushing the entire system to the right. The free body diagram of the system is just the force of the push, acting on the sum of all the 3 masses. You can then get the acceleration of the system is again just force of the push divided by the sum of the masses, which should be the exact same number as before. Then each individual box must also have that same exact acceleration, else the boxes might move apart from one another. So in that case, that allows you to get the internal contact forces between the boxes. All right, that's it.